Hello everyone. Today we'll be discussing about negative temperature coefficient thermistors. So this is the circuit simple for a thermistor and negative temperature is being shown here. This simply means that thermistors are having negative temperature coefficient. There are two types of thermistors available which are having positive temperature coefficient as well as the one we are dealing right now, that is a negative temperature coefficient. And here the working is very simple. As the temperature varies, resistance also varies. So that change in resistance is being recorded as an analogous voltage, and that voltage can be an indication of the change in temperature. Now this is having a negative temperature coefficient CARA, that is resistance decreases as the core temperature of the resistor increases, and the operating range is shown here. It is from -60 to the range of 15 degrees, and the operating range is very small, and these are used as temperature sensors as well as current limiting devices. In both the cases you are using this NTCs. It is also used for temperature measurement as well as control and compensation, and the resistance range is from 0.5 ohm to 0.75 mega ohm. So you have resistors of this range available. Now these are some of the commercial forms of thermistors which are available. Here you can see that you have a bead type, a probe type, a disc type, rod type. Okay, so these are all different types of thermistors which are available, and these are all composed of synthetic mixture of metal oxides such as manganese, nickel, cobalt, copper, iron, uranium. So it's a mixture, and this is being formed in the shape of a bead, and you have leads attached, and these leads will be carrying the current in and out into this bead. So different shapes and sizes are available depending on the application that you choose. Now first we will take up the resistance temperature characteristics. So this is general relationship for resistance of a thermistor. RT1 is equal to RT2 e raised to beta into 1 by T1 minus 1 by T2, where T1 is a temperature at beta is depending on the material of the thermistor, and typically the beta varies from 3500 to 4500 degree Kelvin. Now NTC exhibits negative temperature characteristics that you can see here. As the temperature is changing, say it is changing from in the range from say 0 to 200 degrees suppose, or you have a variation in range of 0 to 400 degrees. So in such a scenario, your platinum resistance is also shown here. Your platinum resistance is a positive temperature coefficient, RTD, resistance temperature detector. So the resistance is varying in this range, but you can see that for a thermistor, resistance varies in the range of 10 raised to, this is almost 10 raised to 5, 10 raised to 5 to 10 raised to minus 2. So within that small change in temperature, your resistance is varying drastically or in a large manner. So that is one of the main characteristics of a negative temperature coefficient thermistor, where it is highly sensitive to changes in temperature, and you have large variations of resistances available. Now second we'll see the voltage current characteristics. So here you can see that a voltage is being marked, and the current voltage in volts and current in milliamperes. So once you increase the voltage from 0, initially when a small voltage is applied to the thermistor, you will have a small current. Initially there is no temperature change. You have a thermistor, okay, and this thermistor, okay, is being supplied with the voltage source, and some current will be flowing, and this current will be very small initially because temperature of the thermistor is not changing. It is almost constant, and the voltage is slowly increasing, and it acts as a normal resistor, and the current is also increasing. So you can see that initially your voltage is proportional to current, and it follows a linear relationship, and it follows Ohm's law. V is equal to IR. And as the current increases with the increase in applied voltage, that heating effect increases. That is, you will have losses in this particular resistor. You will have I squared R losses, and it starts dissipating or starts heating up. Once the temperature increases, what happens? The resistance reduces, and once the resistance reduces, you will have larger currents still flowing, because once the resistance is reducing with the voltage increasing, the current increases. So the voltage across the thermistor will rise to a maximum value and then decrease, because you have a heavy reduction in resistance, and the current is still increasing. So current is increasing and the resistance is reducing, and so your voltage increases and then drops, and the current will continue to increase. It is not that current increases infinitely. The current will continue to increase as long as there is a change in resistance, and after some time, and the resistance will be settling to some particular value. Here you can see that after your resistance is now coming to a steady state, you have a constant region here. So in the same way, your resistance is coming to a steady state, or change in resistance is reduced to 0. You will have a steady state when the power dissipation is balancing with the power that is applied to the resistor. That is, you have equal power dissipation and power input, your resistance will not change further, because whatever the heat that is produced, that is released, and you have no change in temperature. So in such a condition, whatever the heat that is produced within the resistor, that is being dissipated, and you have a steady state in terms of temperature, you have a steady state in terms of resistance. So your current will increase only up to that point. So that's why you have a curve like this. Now you have another curve which determines the carrier between current and time. So initially you can see that there is a time delay for current to reach maximum value. Here a different curve indicates different voltages being applied across this thermistor, and you can see that the current will be increasing to maximum value slowly. There is a time delay for the current to increase to maximum value. That is because once you increase the applied voltage, the current will be increasing slowly, and with time you can see that current will be increasing slowly and reaches a maximum value, and then it remains steady. So here the resistance also remains steady, becomes steady only after some time, because there is, due to the heating effect and due to the power dissipation, there is a finite time up to which your resistance will change, and then the resistance will remain steady. So your current also will become a maximum steady state condition, or reaches a maximum steady state condition only after some time. So there is a time delay. So the time delay can be in terms of milliseconds or even seconds in case of thermistor. Now some of the applications of this thermistor can be used as a measurement of temperature with the help of a potential divider circuit. So once the temperature of this particular thermistor changes, the resistance changes, and you get an output voltage in terms of resistance of the thermistor. So that output voltage can be an indication of the temperature that is being changing. Now it can also be used as a temperature control mechanism and alarm. That is, once the temperature is increasing, the resistance reduces, and once the resistance falls below a particular value, it can be recorded, and an alarm can be initiated. Once the temperature goes beyond a particular value, that is, the resistance falls below a particular value. In such a way, you can have a temperature control mechanism with the help of this thermistor. Another mechanism is you can measure the flow of fluids. That is one interesting mechanism. So this simply happens because or depending on the Cara of self-heating mechanism. That is once, as you have seen, with increase in your thermistor Cara will be looking like something like this, resistance versus temperature. So the resistance reaches a steady state value after some time. The reason is that the heat dissipation is balancing with the heat that is provided into this resistor, or input heat into this resistor, so that once the flow of fluid is able to remove the heat from the thyristor efficiently in a steady state manner, the temperature will not increase and the resistance remains same. And if heat dissipation is not occurring properly, there will be a change in temperature of the thyristor, thermistor, and this particular change in heat or temperature can be identified as a change in resistance. Hence, the fluid flow also can be identified with the help of this heat dissipation property of the this particular thermistor. So these thermistors have certain advantages. They are more sensitive when compared to other sensors. They have high sensitivity. They have low cost and cheap to replace. They have fast response. They are easy to use. The size is very small, and they come in standard two-way connections which are compatible, and they can be easily interfaced with the electronic systems. And some of the drawbacks is that they need shielding from power lines. That is, high voltage lines shielding is required while using thermistors in near to power lines, and excitation current should be low in order to avoid self-heating. Again, you need an external power source to drive this, operate this particular mechanism or the thermistor. And once the current increases, your self-heating effect also increases, and it leads to a reduction in resistance. So that should be avoided. And it is not suitable for very large temperature range. And as you can see, the temperature Cara is not linear. They are showing a non-linear fashion or non-linear shape. So these are some of the drawbacks that you can think about related to thermistors. So thank you so much.